Artemis II is in danger, and for 4 minutes, no one will be able to help. When Orion hits the atmosphere at 40,000 kilometers per hour, the air around it will ionize into a sheath of plasma so dense that every radio signal is blocked. The crew will see the windows glow white. They'll feel the G-forces mount. They'll hear the atmosphere ripping apart around them. And in Houston, every screen in mission control will go dark.
Nothing. No signal.
If the heat shield holds, the signal comes back. If it doesn't, the silence just keeps going. Reid Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen launched from Kennedy Space Center on April 1, 2026, aboard the most powerful rocket NASA has ever built. They are the first humans to leave Earth orbit since Apollo 17 in December 1972. The first woman beyond low Earth orbit, the first black man, the first Canadian. Their spacecraft will carry them over 406,000 kilometers from Earth and roughly 7,600 kilometers past the far side of the Moon, farther than any human being has ever traveled. And every single meter of that record-breaking distance has to be paid back in full during re-entry. Getting to the Moon is a problem of propulsion. Getting home is a problem of survival. The part of this mission that keeps engineers awake at night isn't the launch, which went almost suspiciously well. It isn't the trans-lunar injection burn that sent Orion hurtling toward the Moon at escape velocity. It isn't the 50 minutes of radio silence as the crew passes behind the far side, where no signal from Earth can reach them. It's the last 10 minutes of the entire 10-day journey. Specifically, a window of roughly 4 minutes during peak atmospheric re-entry, when the exterior of the capsule reaches temperatures above 2,760 degrees Celsius, the crew loses all contact with mission control, and the heat shield either works or it doesn't. There is no abort option, no backup plan, no second attempt. If something goes wrong during those 4 minutes, no one on the ground can do anything about it, and the crew won't have time to do anything about it either. A capsule returning from the International Space Station re-enters at roughly 28,000 kilometers per hour. That's fast, but the thermal loads are well understood across hundreds of missions. Orion will re-enter at just over 40,000 kilometers per hour. Mach 32. 32 times the speed of sound, the fastest any human being has ever traveled. At those velocities, the air molecules in front of the capsule can't get out of the way. They compress into a shock wave, superheat, and ionize into plasma. The temperature on the face of the heat shield climbs past 2,760 degrees Celsius. For reference, structural steel melts at about 1,370. Titanium fails around 1,670. The carbon fiber and titanium skeleton of Orion's crew module would be liquid in under a second without protection. That protection has a name: Avcoat. Avcoat is what engineers call an ablative heat shield, designed to destroy itself on purpose. As the spacecraft slams into the upper atmosphere, the outermost layer chars under the extreme heat. That charring absorbs enormous amounts of thermal energy. The char then erodes away into the airstream, carrying the absorbed heat with it. Layer by layer, the shield sacrifices itself so the structure underneath stays cool enough to survive. NASA used Avcoat on every Apollo command module that brought astronauts home from the Moon between 1968 and 1972. It worked flawlessly every single time. So when Orion needed a heat shield capable of handling lunar return velocities, they went back to what they knew. They probably should have been less confident. The original Apollo heat shields were manufactured as a single honeycomb structure, containing roughly 320,000 tiny hexagonal cells, each one filled by hand with Avcoat material. Painstaking work that took months. For Orion, Lockheed Martin simplified the process. Instead of filling hundreds of thousands of individual cells, they manufactured about 186 pre-machined Avcoat blocks, each designed to fit a specific position on the heat shield's 5-meter-wide carbon fiber skin. The blocks are bonded into place like pieces of a puzzle. It saved enormous amounts of time. Whether it preserved the same thermal performance was a question nobody could answer until the shield flew. In November 2022, it flew. Artemis I sent an uncrewed Orion on a 25-day journey around the moon and back. By nearly every metric, a triumph. The celebration lasted until engineers got the capsule back to Kennedy Space Center and peeled the heat shield off for inspection. Over 100 locations showed unexpected damage. Large sections of charred Avcoat had cracked and broken away in irregular chunks, not the controlled, even ablation that decades of ground testing predicted, but jagged, unpredictable material loss that in some areas had exposed layers never supposed to encounter re-entry temperatures directly. The pattern correlated with something very particular about the way Orion had come home. Artemis I used a maneuver called skip re-entry. Instead of diving straight into the atmosphere, the capsule first dipped in to shed velocity through aerodynamic drag. It then used its aerodynamic lift to skip back above the atmosphere, like a flat stone bouncing off a pond. After a brief coast in near vacuum, it dipped back down for a final descent. The advantage is precision, extending the distance the capsule can travel during descent to give mission planners flexibility in choosing a splashdown location. Apollo never had this. Skip re-entry was supposed to be the modern upgrade. Inside the Avcoat, it was catastrophic. During the skip phase, when the capsule climbed back above the atmosphere, external heating dropped sharply. That triggered a chain reaction. Avcoat produces gases internally during ablation through pyrolysis, essentially burning without oxygen. Under sustained high heat, those gases vent outward through the porous char layer. The system is self-regulating, but when heating paused during the skip, the char layer became denser, less porous, less permeable. The Avcoat underneath was still warm enough to keep producing gas. That gas had nowhere to go. Pressure built inside the blocks, and when the capsule plunged back for the second pass, those pressurized pockets ruptured, blowing charred material off the shield in chunks. There's a detail in the investigation that doesn't get talked about enough. Even with over 100 locations of unexpected char loss, the temperature inside the Orion cabin never exceeded the mid-70s Fahrenheit. The thermal performance exceeded expectations. The Avcoat was doing its job blocking heat. The problem was that the material was tearing itself apart while doing it, and no one could predict where or how much would come off next. An ablative shield with unpredictable ablation is like a parachute that opens but might have random holes in it. It'll probably slow you down, you just can't be certain how much. NASA did not replace the heat shield for Artemis II. The shield was already built, already bonded to the crew module, and replacing it would have added years to a program that had already slipped from 2024 to 2025 to 2026. Through a cascade of technical delays, weather disruptions, and hydrogen leaks during dress rehearsals. Jared Isaacman, the NASA administrator who personally flew to orbit aboard a SpaceX Dragon on the Polaris Dawn mission and understands spaceflight risk from the inside of a pressure suit rather than behind a desk, reviewed the data and accepted the plan to fly as is. Instead of rebuilding, NASA changed the flight plan. The skip re-entry has been eliminated entirely. Orion will fly a steeper, more direct descent, hitting the atmosphere harder, but for a shorter duration. No pause in the middle, no moment where trapped gases can accumulate and fracture the shield from within. The trade-off is significant. Higher G-forces, greater structural loads, more intense peak heating, a less flexible splashdown zone. NASA tested Avcoat samples under the modified profile conditions in refurbished ArcJet facilities at Ames Research Center. They modeled scenarios where the heat shield lost far more material than Artemis I experienced, and in every simulation, cabin integrity held. The agency's own estimate for overall mission risk falls somewhere between 1 in 2 and 1 in 50. At the optimistic end, that's roughly a 2% chance of crew loss. At the other end, it's a coin flip. NASA's official threshold for acceptable risk on Artemis missions is 1 in 30. Rick Henfling is the lead entry flight director. His entire focus for this mission is getting the crew through re-entry alive. He runs the team in Houston that monitors every parameter of the descent in real time. Except during the most critical window, he won't be able to do any of that. That blackout has haunted human spaceflight since the Mercury program in the early 1960s. At hypersonic speeds, the plasma sheath absorbs and reflects radio waves across virtually every usable frequency band. No signal gets in, no signal gets out. For roughly 4 minutes during peak heating, Rick Henfling and every flight controller in Houston will sit at their consoles, staring at screens that show nothing, and wait. During those 4 minutes, sealed inside a capsule heated to the edge of its design limits, the crew will have nothing to do but trust the engineering and wait for the plasma to thin. In April 1970, the crew of Apollo 13 re-entered after their service module was crippled by an oxygen tank explosion. Nobody knew if the heat shield on the command module had been compromised by the blast. The expected blackout was 3 minutes. It stretched past 4, then 5, then 6. Gene Kranz and his team sat in total silence, watching a clock and a blank screen. When Charlie Duke finally heard Jack Swigert's voice cut through the static, the room broke. 33 years later, Columbia broke apart during re-entry on February 1st, 2003, because a piece of foam insulation had struck the thermal protection tiles on the wing's leading edge during launch, and nobody caught it in time. The crew never received a warning. Mission Control didn't know until the telemetry vanished and never came back. Heat shield failure during re-entry is not a theoretical risk. It has killed 7 people. There's something about re-entry that no other phase of spaceflight shares. Launch is violent, but it's a beginning, full of thrust and noise and the raw energy of leaving. The coast between Earth and the Moon is quiet. Wiseman told reporters during a live downlink that he watched the entire globe from pole to pole as the sun set behind it, and the way he paused mid-sentence made it clear the experience had outrun his vocabulary. But re-entry is a reckoning. The angle has to be exactly right. Too shallow and the capsule skips off the atmosphere and vanishes into deep space forever. Too steep and the G-forces, or heating, exceed what the vehicle and the crew can tolerate. The shield has to hold. The parachutes have to deploy in sequence. The cabin has to stay sealed. Everything happens in minutes, not hours, while falling at speeds that turn air into fire. Orion's heat shield measures 5 meters across, the largest ablative shield ever constructed for a crewed spacecraft. Those 186 Avcoat blocks range from about 2.5 to 7.5 centimeters thick. That's the margin. A few centimeters of a material engineered to burn at a precisely controlled rate, standing between 4 human beings and plasma that would vaporize exposed metal before the brain could register what was happening. After peak heating, assuming the shield holds, Orion will still be falling fast. At roughly 7,600 meters altitude, 2 drogue parachutes deploy to stabilize the capsule and slow it from about 480 kilometers per hour. Then, 3 pilot parachutes pull out 3 enormous main canopies, bringing the descent rate down to approximately 27 kilometers per hour. Splashdown is planned in the Pacific Ocean off the coast of San Diego, where a US Navy amphibious transport dock will be waiting. If it works, Artemis II will have proven something the entire future of American lunar exploration depends on. Not just that Orion can fly to the moon and back. Artemis I already showed that. What Artemis II must demonstrate is that Orion can bring people home from deep space, that the heat shield can protect a crew under the most extreme thermal environment any crewed vehicle has ever faced, and that the modified reentry profile solved the gas pressure problem. Artemis III, the mission that will actually land astronauts on the lunar surface, cannot fly until Artemis II proves the ride home is survivable. There's another dimension to this mission's risk beneath the heat shield story. The crew launched during the peak of solar cycle 25, when the sun is at its most volatile. Beyond the Van Allen belt, a single large solar particle event could deliver a significant radiation dose. Orion has a small radiation shelter within the capsule, the most shielded corner the crew can crowd into if a solar storm erupts. Whether that shelter is adequate for a worst-case event has never been tested with humans aboard. All 4 crew members reviewed the heat shield investigation. They saw the photographs of the Artemis I damage. They studied the modified descent profile, the risk numbers, the test data. They understood what 1 in 50 means and what 1 in 2 means. They got in the capsule anyway. Reid Wiseman spent years landing fighter jets on aircraft carrier decks at night, which is essentially parking a car going 250 kilometers per hour onto a moving platform the size of a tennis court, in the dark, over open ocean. Victor Glover flew combat missions and has already lived aboard the International Space Station. Christina Koch spent 328 consecutive days in orbit, at the time the longest single spaceflight by a woman. Jeremy Hansen is a former CF-18 fighter pilot and the only member of the crew who has never been to space. Around April 10th, Orion will reach entry interface, 122,000 meters above Earth's surface, where atmosphere becomes thick enough to matter. The European-built service module, which has provided power, propulsion, water, and breathable air for the entire mission, will separate from the crew module and burn up in the atmosphere behind them. Everything disposable gets thrown away before re-entry. The launch abort system, the solid rocket boosters, the core stage engines, the service module. One by one, every component of the 30-story rocket that carried 4 people off the surface of the Earth has been discarded, until all that remains is a capsule roughly the size of a large SUV, falling alone. Orion will rotate until the heat shield faces the direction of travel. The guidance computer will take over, making micro-adjustments to the capsule's angle of attack, using small reaction control thrusters, trimming the trajectory toward the splashdown zone. Within 90 seconds, the temperature will cross 2,000 degrees. Plasma will close around the capsule like a fist, and then, exactly as promised, the radio will die. For 4 minutes, the crew of Artemis II will be alone with physics. No ground support, no telemetry link. In Houston, Rick Henfling and his team will watch blank screens and count seconds. They've trained for this silence. Simulation is not the same as the real thing, but they know that. Everybody in that room knows that. When the signal comes back, when that first fragment of voice or data punches through the thinning plasma, every person in mission control will know the answer to the only question that has mattered since this mission was conceived. The shield held, or it didn't. 54 years ago, we stopped going to the moon. We had the technology, we had the rockets, we had astronauts willing to fly. But we stopped, and for more than half a century, the farthest humans ventured was a few hundred kilometers above Earth's surface, circling in low orbit, close enough to see city lights at night. Artemis II is the first step back. Not a giant leap, a proof of concept. 4 people flying a vehicle that has never carried a crew around a destination humanity abandoned 2 generations ago, protected by a shield that didn't behave the way it was supposed to last time. Everything that comes after, every lunar landing, every long-duration stay on the surface, every piece of infrastructure we build beyond Earth depends on what happens in the next few days. If the signal comes back, the moon becomes a destination again. If it doesn't, everything stops. We'll know soon. Thanks for watching, and I'll see you in the next one.